All right, so this is the lab solar system models. I'm going to kind of work through this, thinking maybe I'm expecting too much out of you guys. I don't know, but anyway, background material. Review the geocentric model background material. The simulation of Ptolemy's model demonstrates the dominant model when Copernicus presented his heliocentric model. Thoroughly review the heliocentric model background material. So let's take a look. All right, so what we see, basic observations. Man has looked up into the sky for countless ages, but many are not simply content to admire its majesty, but yearn to understand it. To help us understand the heavens, we create models or representations, which, while simplified, but retain the key elements. It is through models that astronomers understand most phenomenon, from the stars to galaxies to the universe as a whole. We've been doing it for a long time, but the basic processes of modeling remains the same. Observe and describe those observations as part of a model. What are some of the astronomical observations we see? All objects in the heaven rise in the east and set in the west. The sun travels around the sky in 24 hours. The stars travel around the sky slightly faster than the sun, 23 hours and 56 minutes. There are several thousand stars that we can see at night with good visibility. There are many ways to describe these events. For example, we could say that bright luminous God, pulling a chariot with a vast drapery of stars, flies through the heavens in a great circle, creating day and night. But that wouldn't be very satisfactory to us, nor was it satisfactory to the ancient Greeks. The model of the heavens. To model the heavens, we need a model of the earth. Many in the ancient world believed it was round. Some of the earliest records come from the ancient Greeks. Through other cultures, though other cultures were aware of Earth's sphere, that Earth was a sphere. Pythagoreans and Plato, for example, taught that the Earth was round. Aristotle recorded several observations arguing for a round Earth. The lower part of a ship disappears. These are Aristotle's theories or observations. The lower part of a ship, and you should be familiar with these, disappears below the horizon. First, different stars are visible to different observers, and the paths they take is different. This implies that up is in a different direction, as would be the case for those on spherical surfaces. The shadow of Earth on the moon during a lunar eclipse are consistent with the Earth being a sphere. Several ancient Greeks even measured the radius of the Earth. Eratosthenes is perhaps the most famous. Due to a serendipitous calculation of errors, he came up with a value that was extremely close to the accepted value of the Earth's circumference, 24,900 miles. Other Greeks used more sophisticated and correct methods and got significantly smaller values, which initially led to Christopher Columbus to believe he could successfully traverse west across the Atlantic to Asia. The sun and the stars, the planets. The sun and the stars move across the sky in regular, predictable way. The stars move slightly faster than the sun, about 4 minutes a day, or 1 degree a day. The planets Mercury, Venus, Mars, Jupiter, and Saturn, however, behave differently. The following observations apply to them. Mercury and Venus were only seen near sunrise or sunset. Mars, Jupiter, and Saturn usually move slower than the stars. And sometimes Mars, Jupiter, Saturn move faster than the stars. Retrograde motion. Retrograde motion varied slightly in when and how long it would last. It is precisely this reason that the planets have their name, which in Greek means wanderers. The challenge was how to observe them, and Plato is reported to have put forth the challenge to do so with simple, uniform, circular motion. Okay, to make a good model of the solar system, and of course that's the name of this lab, solar system models, we need to know what elongation is. To make a good model of the solar system requires good observations. Good observations require a good way to talk about them. Planets were referred to their positions in two ways. The first was the location of the planet with respect to the stars. For example, the planet could be said to be in the constellation Sagittarius. Because the planets tended to move slower than the stars, which constellation the planet was next to would change the time, much as the sun did. Would change with time, much as the sun did. The next way to talk about the planets was its position with respect to the sun. The angle between the sun and the planet is called elongation. Venus and Mercury. And you can see right here what elongation is. We'll just say here's a planet, and you can see this angle is called the elongation of a planet, right? The angle between the person that's looking towards the sun and then the planet. Venus and Mercury were always seen near the sun, either right before sunrise or right after sunset. Indeed, it took a while for the ancient Greeks to realize these morning and evening stars were the same planet. Another way of saying that Mercury and Venus were always near the sun is that their elongations are small. The largest value it would reach is called the greatest elongation. It is during greatest elongation that they would be the easiest to see. The greatest elongation of Mercury is about 28 degrees. The image above combines several shots of Mercury to illustrate its successive positions during March of 2000. Each picture was taken from the same location in Spain when the sun was 10 degrees below the horizon. The images were combined on a single, most vibrant sunset. Mercury's position at the top of the arc would correspond to the greatest elongation. So, right here is greatest elongation. These top spots are greatest elongations, okay? And these are different degrees, different elongations. Venus is easier to observe than Mercury because it has a larger, greater elongation. So we can see Venus better because its elongation, it has a larger angle, 48 degrees instead of 28. When Mercury and Venus have an elongation of 0, they are said to be in conjunction. Superior conjunction if the sun is in front of the planet, and inferior conjunction if the planet is in front of the sun. Mars, Jupiter, and Saturn. Now remember, Mercury and Venus are between the sun and the earth. They're closer to the sun. They're closer to the sun than the earth is. So they're going to have a little bit different pattern than the planets outside of the earth that are farther out than the earth, Mars, Jupiter, and Saturn. Those planets could be seen far from the sun, specifically when the sun was on the opposite of the earth than the planet, or in an elongation of 180 degrees. The planet was said to be in opposition. When the planet was aligned with the sun, elongation of 0, it was in conjunction. When the elongation was 90 degrees, it was said to be in a quadrature. Quadrature because it was 90 degrees, 180. Those are 4 parts of that circle. It was during opposition that these 3 planets tended to undergo retrograde motion. Mars had the most dramatic and difficult model to retrograde. And here they are. Notice how Mars is moving here. And then it starts going backwards and then back forwards. All right, the retrograde motion of Mars. Each dot represents the position of Mars with respect to the stars 2 weeks later, starting from August 24th. All right, so now we've looked at these first 2 pages. Elongation and basic observations. We're going to go on to early modeling, Ptolemy's model simulator. All right, so this is Ptolemy's model, or Ptolemy. I don't know why I always put the P on there. It's Ptolemy, but spheres within spheres. The sky, and this helps explain retrograde motion. This is what they thought might be happening in a geocentric. That means the Earth is in the middle. Here's the sun out here cruising around, and here's the planets. The planets will make little circles around an invisible object as they go around the Earth. So they're going to orbit like this. Okay. So the sky moved in a regular way, but there was a few irregularities, chiefly among them the retrograde motion of the planets. The ancient modelers of the cosmos were quite challenged by how to address them. For several reasons, circles were the tool of choice. The heavens were to be thought of as a sphere within spheres. Specifically, the Earth was placed at the center and was surrounded by numerous concentric crystalline spheres. The spheres rotated at different rates along different axes, allowing the sun and the planets to move slower than the stars. But this model did an inadequate job of explaining retrograde motion, even with many shells. Aristotle's model, for example, had some 55 crystal spheres. Ptolemy. To help deal with the problem of retrograde motion, a new layer of complexity was introduced. The planets would not move simply in a circle, but they would rotate on a circle, which in turn rotated around the sun. The smaller circle is the epicycle, and the larger circle is the different. Claudius Ptolemy, we call him Ptolemy, lived from 90 to 167 and worked with this system. But even the simple addition of the epicycle was not enough. The epicycle had to rotate around the different, not with respect to the center, but uniformly with respect to an off-center point called the equant, right here. Ptolemy's model was astoundingly successful in so much as it dominated astronomy for over 1,000 years, but was the model to which most all other deferred or sought to improve. But it was the cumbersome and burdensome model which lost accuracy with time. The following simulator shows some of the complexity of the Ptolemy or the Ptolemy's model. Okay, so here's the Ptolemaic system simulator. And here would be the Earth. The sun's out here. And if we start the animation, you can see how they used to believe the planets would orbit the Earth. And where it starts to move backwards right here, that is retrograde motion. All right, where it does that little extra loop. Retrograde motion is starting to move in the opposite direction, makes a little loop. So that's the way they thought the planets orbited Earth at one time. And that's the only way they could show retrograde motion. Along came Copernicus and the heliocentric universe. That is, the sun is in the middle, or is being orbited instead of Earth. The idea of placing the sun at the center of the universe was not a particularly new one, but few either saw advantages to it, and many considered it physically impossible. It was inconsistent with Aristotle. That started to change with a Polish physician, lawyer, artist, and astronomer, Nicholas Copernicus. Copernicus was aware of earlier writings which suggested a moving Earth. He, however, seemed to be motivated by two main suggestions. One, he believed that the Earth was not a particularly fit object to be the center of the universe, but the sun was a more divine object and thus more fit to be the center. Second, Copernicus very much disliked the concept of equant. He thought it was an abomination and a betrayal of the concept of circles. He appears to have been aware of works by Arabic mathematicians who, in an attempt to reconcile with the Quran, which suggests the Earth moved, with a Ptolemaic system, removed the equant in favor of additional epicycles. Copernicus likewise used epicycles in his calculations, but no equant. What really set Copernicus' heliocentric model apart was its simplicity. It did no better than Ptolemy's model at predicting the planets, but it was easier to use and handle. While few actually read Copernicus's deathbed publication of his works, De how on the revolutions of the heavenly spheres, it did gain a few fans, such as Galileo. So what Copernicus did is he recanted everything. He said, "Nah, I don't believe this," because he was going to be, um, dealt um, with the church probably unfavorably. So he waited until he was on his deathbed before he published his works. All right. And he did that. He was going to die anyway. So why not do it? Okay. That's what he thought. So observations explained. Copernicus's model handled the basic observations. Like the geocentric model, the Earth was believed to be round. The Earth rotated. Thus, the stars, sun, and planets appeared to move around the Earth. Mercury and Venus were closer to the sun than the Earth, and so always appear near the sun. As the Earth passes, or as the Earth passed Mars, Jupiter, and Saturn during opposition, the planets would appear to undergo retrograde motion. It explained the same phenomenon as the Ptolemaic model did, but so much more simply. This made it attractive to some. The next background page, Elongations and Configurations, describes the models and the observations that provide data. Elongations and configurations. Elongations. In Copernicus's heliocentric model, the planets orbit in circles around the sun. One may wonder how Copernicus determined the order of the planets and the size of their orbits. After all, he had no benefit of pictures from spacecrafts or even a telescope. He determined these things by measuring elongation. Elongation is the angle between the sun and a planet as seen by an observer on Earth. Imagine that you could see Venus and the sun at the same time. To measure the elongation of Venus, you could hold a piece of paper so that its flat edge is in line with the two objects. Then you would draw a line pointing to Venus and a line pointing to the sun. Measuring the angle between the two lines gives you the elongation of Venus. Looking at directly at the sun is not recommended, obviously. But for instance, if the sun and a planet are at the same point, then the elongation is 0. If a planet is at the opposite point in the sky from the sun, it has an elongation of 180 degrees. However, some planets will never have such an elongation. To see why, we need to consider the difference between inferior planets and superior planets. If we could look down on the solar system from a distant point in space, we would see that some of the planets are closer to the sun than the Earth, and some are farther away. The ones that are closer are called inferior planets. Those are the planets between Earth and the Sun, Venus and Mercury. The ones that are closer are called inferior planets. The ones that are farther away are called superior planets. Also note that from this perspective, elongation is the angle between the Sun, the Earth, and a planet. All right. So here we are. Here's superior planets. They're farther away than the Earth. And inferior planets, planets that are closer to the sun. And let's take a look at how this works. Now, if we look at this, we're about to hit superior conjunction. They all lined up. All right. This is a planet that is it's an inferior planet. So watch again as it's coming around. Here comes greatest elongation. Right there. It's as far away as it ever gets. Now it's going to come back up to inferior conjunction. Superior conjunction is when it's on the opposite side at 0 degrees. All right. There's the greatest elongation again, west this time. And it is a little bit different because when the planet's on the right hand, it's on the west. And here comes superior conjunction. Boom. We can't see it. It's back here. Going to come to, now look, we're moving east now. East will be to the left. All right. Now over here and on a superior planet, we're about to come to conjunction. Conjunction. And we don't have inferior conjunction like we do with, it's a little bit different over here, just conjunction. Kept letting it go. Now look, notice this does not have a very great elongation compared to this. Watch, greatest elongation. Look at the degrees. Greatest elongation down here. Or I'm sorry, quadrant. Boom. So they move a little bit differently. All right. Inferior planet configurations. Looking at figure 3, you should be able to see why an inferior planet can never have an elongation of 180 degrees. If it did, that would mean that the planet is farther away from the sun than the Earth. Instead, for an inferior planet, there's a limit called the greatest elongation. This is the maximum angle that ever occurs between the sun and an inferior planet. And it depends on the planet's distance from the sun. Observing that a planet never has an elongation of 180 means that it must be an inferior planet. And this is how Copernicus knew that Venus and Mercury are closer to the sun than the Earth. Further, by using geometry, Copernicus was able to determine the distance of these planets from the sun based on their greatest elongations. Note that there are 2 points at which an inferior planet is at greatest elongation. We differentiate these by observing whether the planet is west or east of the sun at the time. Also note that there are 2 different configurations in which an inferior planet has an elongation of 0 degrees. These are given different names. When the planet is between the sun and the Earth, we say it is at inferior conjunction. When the planet is on the other side of the sun, as seen from the Earth, it's superior conjunction. So again, here comes inferior conjunction right here. When everything's at 0 degrees, watch 0 degrees, boom. Superior conjunction is out here when they line up at 0 degrees again, all right? Superior planets. Unlike interior planets, superior planets can have any elongation value between 0 and 180 degrees. When a superior planet has an elongation of 0 degrees, we say it is at conjunction. Since there is only one type of conjunction for superior planets, we do not need to use the term superior conjunction. An elongation of 180 degrees is called opposition, since the sun and the planet are opposite sides of the Earth. Another special configuration for superior planets is quadrature, which occurs when the planet has an elongation of 90 degrees. As with the greatest elongation, we can specify that a planet is at eastern quadrature or western quadrature. Thus, if a planet never reaches opposition, we know it must be a superior planet. This is how Copernicus decided Mars, Jupiter, and Saturn are farther from the sun than the Earth. The planets Uranus, Neptune, and Pluto were discovered in 1781, 1846, and 1930, respectively, so Copernicus never knew about them. The size of a superior planet's orbit can be determined from elongation measurements, and we're not going to the advanced page right now. All right, sidereal in synodic periods. I'm not sure if this calculator right here works, you guys. I can't remember if it does or not. We'll check it out, but by observing the elongation of planets, Copernicus was able to figure out how far each planet is from the sun. However, he still needed to know how long each planet takes to orbit the sun. The time it takes to complete an orbit is called the sidereal period. If we are at fixed points in space and had enough time, all we would need to do is start a stopwatch and record how long it takes for a planet to return to the same position as when we started. For a human on Earth, this is not practical. First, planets can take a long time to complete their orbits. For instance, Saturn's sidereal period is over 29 years. But a more important factor is that the Earth is orbiting the sun along with the other planets. We do not have a fixed frame of reference, so it's impossible to measure the sidereal period directly. Fortunately, elongation provides an indirect way to calculate the sidereal period. What we need to do is measure the synodic period, The synodic period is the time it takes for a planet to make a complete cycle of elongation configurations. For instance, we can measure the synodic period of Mars by recording the time it takes for Mars to go from one opposition to the next opposition. For Venus, we can record the time it takes to start at and then return to its greatest western elongation. It does not matter which elongation configuration we choose. All that matters is the time it takes to return to the same elongation configuration. Copernicus was able to show that the synodic period of a planet is the sidereal period of the planet and the sidereal period of the Earth are related by one of the following formulas. Now, what it's talking about here is here we come up on that was greatest elongation, but let's wait until it gets to its next point. Right here. Now, we're going to wait and see how long it takes to line back up there again at superior conjunction. All right. That's what you would do. And you take those days and use it that way. Same thing's going to happen here. When it gets to the certain point in conjunction, all right, we will wait to see how long it takes it to get in conjunction again, and then we will know. That's how we can figure out these synodic period. All right. And I'm not going to go into the math of this again. We're going to try to get this to work. If we can't, we'll find one that will work for us. All right. On the last page, it shows Copernicus's equations he used. And again, I'm not going to get into the math, crunching a whole bunch of numbers. And I don't think we have to in this lab regardless. So let's take a look at the lab and let's get started. All right, so let's take a look now at the lab and let's see what's going on here. Background material, we just read all that together. Question 1, look at the animation of the Copernican solar system on the heliocentric page. What relationship do you notice between how fast a planet moves in its orbit and the distance from the sun? All right, well, let's check it out. Here's the Copernican page. Where is it? I believe it's going to be right here. Nope. Oh, right here. There we go. All right. So, what do we notice about these planets? They're cruising around the sun. And the question again, let's look at the question. Look at the animation. What relationship do you notice? How fast a planet moves in its orbit and its distance from the sun? Well, we can tell just by looking at this for a second. The closer the planet is, looks like the faster they move. All right. So the closer the planets are, and as a matter of fact, Earth takes 1 year. I believe Mercury takes 88 days. Okay. So you can see, looks to me like the closer the planets are to the sun, the faster they move. So that's our answer to question number 1. Now, give me a couple of good sentences here. Just don't be, the closer they are, the faster they move. I want a sentence as an answer, at least a sentence, maybe 2. Question number 2. The table below concerns various elongation configurations for a hypothetical superior planet. Remember, superior is beyond Earth's orbit. Complete any missing elongations, terminologies, or lettered labels on the drawing where the sun and the Earth are shown. All right, so the first thing I'm going to do here, and I'm going to try to do this. Hopefully it works, okay? First thing we're going to do is we're going to get our 0. And that would be a line, and I'm going to do the best I can here. I know it's not going to be perfect, but I'm going to try to get it in the middle, pretty close. So that's my 0 point. All right, that's 0 degrees. Now, it's close enough for this. Okay. So elongation. Location A is going to be 180 degrees. 180 degrees. So let's go back and look at elongation again. All right. Okay, so now what I'm going to do, I'm going to come here and I'm going to go to this right here, Planetary Configuration Simulator. We're going to click this in. Let's try to get this lined up like we have it in the lab here. I'm going to just grab and spin the planet, spin the Earth until we're in conjunction, I believe is where we want to be right there. I clicked over here, conjunction. So now we're pretty much set up like this picture. All right. So this was C. It says elongation of 180 degrees. 180 degrees is location A. So let's check that out. Okay, let's see 180 degrees. Boom. Let's click our elongation. Let's put this at 180 degrees. I don't think it says east or west. We're going to find out. Boom, right there, 180 degrees. Okay, there we are. We're there. And so now what we need to do is we need to put A over here. So let's put a little circle in there. Let's see if we can do this. A little circle for our planet. Try that again. And again, just do the best you can. It's not, that's close enough. And we're going to call that A. All right. There we go. There we go. So that's A. Let's just go like this. We'll put a little text box right here. Boom. You put in the letter A. There's A. All right. Okay. So what is this term called? What is it called? Let's go back here. It is called, boom, opposition right here. Opposition. So we're going to write that in. Opposition. Western quadrature. Western quadrature. So now that we have this, all we have to do, this is simple. Let's find Western quadrature. Western quadrature right there. Okay. Now what we have to do though here to make sure, because this is just going to be weird, is we need to consider the Earth back over here. So we just kind of have to take this thing and spin it around. We could actually, let me see something. Yeah, it's not going to work the way I would like it to, but anyway, we'll go to Western quadrature. Boom. All right. And it's going to be 90 degrees to the west, 90 degrees west of the sun, west of the sun. So if we come back here, B would be over here. So let's try to put a little line there. I don't know. It's not going to be perfect. We'd like a 90 degrees, but obviously it's not going to work the way we want it to. Just kind of eyeballing 90 degrees. Boom, close enough. We're going to put another little planet in here, a circle. Just do the best we can. Boom, good. And let's text box that. And we'll say that's B. Boom, B. And I'm going to type in here 90 degrees. You can see it's 90 degrees west. All right. C. Uh-oh. Where's C? C's right here. What do we call that? Well, if we don't remember, let's take a look. Let's go back to where we were at conjunction. Boom, right there. Conjunction. So you're going to type that in. Conjunction. And what is the elongation? The elongation, easy. Whoop. Elongation is simple, 0. There's my elongation, 0. All right. So you guys need to put that in there. Then it says east 120. So if this is west, this is going to be east, and we're going to have to do it about 120. So let's just say, let's draw a line. Again, this is not going to be perfect, you guys, but close enough. There's 90. I don't know, 100. We'll say 120 right there. Good enough. 120 degrees east. And there is nothing but we got to label that. We got to put a little circle there. Boom. Put our little circle in there. Good enough. And we'll call that D. Boom. There we go. First page is done. First page is done. All right. All right. So now we're looking at an inferior planet, a hypothetical inferior planet. All right. We're going to do the same type of thing here. I'm going to set this up right here. Now, this is going to be different. They have these presets. I'm going to look on here real quick and find out what I have to do for to set up a planet, and I will be pausing this. Be right back. Okay, so we want to make sure we're at Earth, and then right here is where we set up whether it's a superior or an inferior planet. We'll just set it. I don't know. Let's just set it at 0.5. That's where I'm going to do it. 0.5. There it is. Okay. There we go. Now let's take a look at this. All right. Elongation, superior conjunction. Well, I think we're already at superior conjunction, and we are. So 0 degrees, 0 degrees, 0 degrees. Now, let's put in that line that shows us our 0. Close enough. All right, let's put a planet at superior conjunction. Boom. Move it around a little bit, whatever we got to do to make it look like that. There we go. Let's put a little box there and say A. A. That's A. That is superior conjunction. Elongation, again, is 0. Inferior conjunction. Well, let's go like this. It'll be just as easy as if we look down here and we move this around. Just click and drag it. Inferior conjunction. Boom, right there. Again, 0 degrees, but this time the planet is here. So on B, this time B is going to be right here. Boom. And we'll put down a little text box there. And we'll say B. Boom. There we go. So we have A, B, C, and C. We need to get that angle there. Let's take a look at where my elongation is. Let's take a look here. Greatest elongation. Is that west or east? I believe that is east. It is. It's east. So let's go greatest elongation. East. Boom. 30 degrees. So we're going to type in 30 degrees there. So, boom. Elongation is up. Elongation is greatest elongation east. You can just put GE east. That'll work because that box is pretty small. And then, right here, greatest elongation. And then our degrees was 30. I'm sorry. 30 degrees, greatest elongation. And then it says at west 20. So let's, if this is 30 degrees here, let's try to figure out a 20 degree. We'll put a line in there. 30, I don't know, right about here, maybe. Close enough. That, again, it does not have to be perfect. Just, try to do the best you can. Boom. Need to move it down a little bit. there. And then we'll put in a little text box and say that is D. And there we go. We're done. That's the hardest part of this lab is going to be doing this stuff. All right. So now question 4. In this exercise, we'll measure the synodic period of Mercury. Set the observer's planet to Earth and the target planet to Mercury. Earth. And the target planet will be Mercury. Okay, there we go. Let's just reset everything. I don't know. Earth, Mercury. There we go. All right. The synodic period of a planet is the time it takes to go from one elongation configuration to the next occurrence of that same configuration. However, it makes sense to use an easily recognized configuration like superior conjunction. Drag a planet or the timeline until Mercury is in superior conjunction. Let's show our elongations. Right now, we are in inferior, so let's go to superior. What it was saying is you can either take Mercury and go like this, or you can just go down here and click Find Superior Conjunction and click it. Boom, there we go. All right, we got that. Now zero the counter. Click the Start Animation, observe the counter. A synodic period is the time that until Mercury is once again at superior conjunction. All right, so we're going to do that. Zero this counter. Here it is right here in years. All right, and let's stop. When it comes to one of these, you'll see what happens now. I hit stop. So when it gets to greatest elongation, it'll stop. Notice the years and the days down there. Boom. And we got to go all the way again to superior conjunction. Boom. All right. Superior conjunction. The counter, 0.322 years or 117 days. 117.6 days. Let's go see what it says. What is the synodic period of Mercury? Well, the synodic period, again, is 0.322 years or 117 days. Make a sentence. Just don't write those numbers down. There are places in this lab where you can write those numbers down, but let's do it this way for now. All right. Give me a sentence here. On to the next page. Question number 5. In the previous exercise, superior conjunction was used as a reference configuration, but in practice, it is not the best elongation configuration to use. Explain why. Why is it not the best? I can tell you right now why it's not the best, because you can't see it. The sun's blocking it, so you can't really see it. And now look, there's like 3 questions here, so you're going to have to give me 3 questions, at least 3 sentences as an answer, okay? Do you get the same results for the synodic period that you got in question 4? Explain why. All right, so when is an inferior planet easiest to observe in the sky? Elongation, right? Elongation, the greatest elongation. Do you get the same result for synodic period you got in question 4? Well, let's check it out. Let's move it to the greatest elongation, zero that counter. All right. See, we can see this planet better now. So now let's go until we get back to the greatest elongation west, and let's see if I have the same amount of days. There I am, back to greatest elongation west. And yes, the same amount of days. So you're going to answer this question in sentence form, 2 to 3 sentences there. All right, use the greatest elongation as a reference configuration to calculate the synodic period of Venus. So let's check out Venus now. We're changing this to Venus. Boom. All right, we're going to zero the counter. We're going to keep it to where it stops. And then let's read this question a little more. Use the greatest elongation as a reference configuration to calculate the synodic period of Venus. Be careful, there are 2 different occurrences of greatest elongation for an inferior planet, eastern and western. Also, record the value of the greatest elongation of Venus. All right, so let's check it out. Okay, so here we go. We are at Greatest elongation west. This is where we're going to start. Okay. We can already say this is the greatest elongation. Look at here. I just now realized greatest elongation of Venus. Greatest elongation, 46.1 degrees. 46.1 degrees. All right. Synodic period of Venus. Let's see how long it takes Venus to get back to the same spot. Make sure you zero your counter. Boom. Boom. There's the greatest elongation. You want to see something really cool now. As this moves, as this, oh, it's not going to work here. Never mind. I'll bring it up later. But all right, let's check this out. Boom. Boom. Back to greatest elongation. Western, it takes 1.570 years. That'll go in here. Or you could write down days. It doesn't matter how many days you write down. It doesn't matter. 1 year, 208 days. You can use either one of these. I wrote down both when I did it, but hey. What general trend do you notice between an inferior planet's distance from the sun and its synodic period? What general trend do you notice? Which one had the shorter, if you look at these two, which one had the shorter synodic period? Right. And obviously that was Mercury. Mercury is 0.322 years, where Venus is 1.570 years. You can look at this two ways, and you could get an answer. The closer the planet is to the sun, the shorter its period. All right. Or the closer it is to the Earth, the longer its synodic period. So I think you can kind of figure out an answer there. All right. Remember, the closer it is to the sun, the faster its period, the shorter its synodic period. The farther away from the sun it gets, the longer, or vice versa. The closer to the Earth, the longer. Farther away from the Earth, the shorter. All right. Question number 7. Now use the simulator to find the value of Mercury's greatest elongation. All right. That should be simple. Let's just go back to Mercury here. We'll reset, zero the counter. Just always zero that counter. It's just easy. We'll just click greatest elongation, 23 degrees. There it is, 23 degrees. All right. Compare the values of the greatest elongation of Mercury and Venus. What relationship do you notice between the value of the greatest elongation of a planet and its distance from the sun? Okay, so yes, no problem. Mercury's closer to the sun. It has a smaller greatest elongation. Then it says, can you create a hypothetical third planet in the simulator to check your reasoning? Sure, let's do that. If Mercury is 0.39, what's Venus? Venus is 0.72. So let's make a one, I don't care, 0.8. There, 47 degrees. Now, Venus was 46 degrees. Mercury was 23 degrees. And since this new planet is out here, this new planet is 47 degrees. So I can answer that question now. Make sure you're answering these questions in sentences. All right, full sentences. No, don't shirk me on the answers now. All right, let's move on to the next page. All right, question 8. Now will we measure the synodic period of Mars? As before, set up Mars in a particular elongation configuration. Zero the counter, then animate the simulator to see how long it takes Mars to return to the same configuration. No problem. Earth, let's go to Mars. Boom. Let's put Mars at the western quadrature. I don't know. Let's just do opposition. It'll probably be easier. Here it is, 180 degrees, opposition. We will zero the counter. Let's see how long it takes to get to opposition again. Boom. Boom. And finally, boom. You can speed this up here too, you guys. I'm just using it, whatever. All right, so we're back to opposition 2.144 years or 2 years, 52.7 days. All right, so that's your synodic period. That's what's going to go right here. Just as with superior conjunction in question 2, conjunction is not the best configuration to observe a superior planet in the sky. Explain why it is and explain which configuration is best for a superior planet. Well, I'm going to tell you, I'm going to help you here. It's because the sun's not reflecting on it. The sun is blocked. The sun's rays are blocked by the earth. So it's going to be harder to see this thing. All right. It's not going to be as easy to see. It's going to be better to see in one of the quadratures. All right. Because you get a nice reflection off the sun. That is your answer here. Make sure you put that in sentence form. All right. And I need a couple of sentences. Just don't make it blah, 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 blah. All right. All right. Measure the synodic period of Jupiter and Saturn. So now we're going to zero out that counter. We are going to put Jupiter here. Let's put it in opposition. Boom, 0. Let's check that animation. How long will it take it to get back to opposition? Notice how fast the Earth moves around there, right? So check it out. It's back in opposition in a year. 1 point. So that would be Jupiter. Let's check out Saturn. Saturn, where are you? And we're already in opposition. Zero that counter. 1.035 years. Okay. We're going to write that down here. Look over the synodic periods of the superior planets. Is there a trend? Absolutely. What value does synodic period of a superior planet approach when we consider planets farther and farther away from the Earth? Explain. I'm just going to go like this real quick. Let's get something. We have them both. So the farther away they get, what's happening? Look at your times and you can figure that out. Okay. You should be able to figure that out. Give me some good answers here. I have 2 questions. So I need 2 to 3 sentences for an answer. Compare your answers above and your answer to the last part of question 5. And then state a relationship between a planet's synodic period and its distance from Earth. That is valid for both inferior and superior planets. So you're looking at the Earth now, and you're going to have to tie inferior and superior planets together to get an answer here. All right. Again, sentence form. Don't give me no garbage. All right. I want a nice sentence. Okay, so far we've only considered elongation of planets as viewed from Earth. Suppose you were standing on Mars watching the planet go through their motion. Could you use the same terminology as before to explain the configurations of other planets? Yes, you could. The only difference would be that there is an additional inferior planet, the Earth. As an observer on Mars, you would see the Earth go through the same configuration as any other inferior planet. For example, when the Earth appears on the opposite side of the Sun, as viewed from Mars, it's at superior conjunction. When the Earth appears at superior conjunction from Mars, at what configuration does Mars have to be seen from Earth? Let's check it out. Okay, so what I've done is I've set the observer's planet to Mars, target planet Earth. Here's Mars, here's Earth, and if Earth is in superior conjunction from Earth, Mars is in conjunction. So the answer here is conjunction, but again, you need to give me sentence forms here. All right. So when Earth is at superior conjunction, Mars is in conjunction. All right. Set up the simulator so the Earth appears as a superior conjunction from Mars. And time how long it takes the Earth to return to the same elongation configuration. That is the synodic period of Earth as observed from Mars. Record the synodic period of the Earth as viewed from Mars. Okay, so let's zero out. And let's start until we come back to superior conjunction. Boom, boom, boom. There it is. 2.144 years. You're going to write this down. And this can be a simple, 2 point, just like we were doing on these blanks up here. That'll work on that question right there. Okay. How does this answer compare with the synodic period of Mars found in question 8? Explain why they are related. Okay. So compare Earth to Mars and then Mars to Earth, and then give me a comparison here. Okay, for this next exercise right here, it shows these calculations, but we don't have to do this. We're just going to go to this right here. Go to elongations and configurations. Boom. Scroll all the way down. You're going to find this. Now, if this doesn't work for you, I think sometimes it doesn't work. It's working for me because I'm on my laptop. It might not work for you, right? But let's take a look. And it says here, first off, Mercury. And we know Mercury is an inferior planet, so we're going to have to click inferior here. That might be where it does not work. So anyway, let's try it and see what happens. So synodic period of Mercury, we're going to go back up, scroll back up, and find out what our synodic period was for Mercury. I'm flipping right now through my lab. 117.6 days, or well, that's what I have as days. 117.6 days. I should have. Let me just do this again. Let's get this. You probably have it written down. Let me flip through my lab that I have here, and I'll get right back. I'm going to pause. Okay, I've got it. It's 0.322 years. I want to see if this is going to work. So you're going to put that synodic period in here, 0.322 years. Ouch. It's not going to work because I cannot click on an inferior planet on this. So let me pull up a new. I knew there was something wrong with this and I couldn't remember what it is, but that's it. So let me pause and I will pull one up online and we'll come back. Okay, here we go. We've got it now. I pulled one up, and you can just look one up. Believe it or not, I didn't realize it, but here's the new one. They realized this one didn't work. Notice here's a new one. So this is an inferior planet. We're going to click the sidereal day or 0.322. Earth is going to be there. We will enter. All right, I was having trouble with this thing. Make sure you reset it up here. Okay, hit that reset button to get it back to where it's supposed to be. So, inferior 0.322, and well, this one's not working either. Let me find another one. All right, now I found one that works, and again, it looks like it's right through the same thing, but this looks like the original one we had. So let's just use this one. Again, search, I think it was the third one down, but we're an inferior planet and it's 0.322 years. Okay, and we can see that the, get to the right page here on my lab. So, Mercury, synodic period 0.322, and the sidereal period is 0.24 years. And that's all you have to do with these. Just make sure you're clicking inferior superior. Okay. If we did a superior planet, let's say we do, trying to find one in my paperwork here. Mars. 2.144 years, and the side rail is going to be 1.87. So that's all you have to do to fill these out. Okay, it's easy. It's going to be easy stuff. Easy stuff. All right. After you fill this in, you're going to look at the relationships and answer this question, 2 questions, again, in sentence form. Question 14. Put yourself on the planet Mars and carefully note the location of the sun on the zodiac strip. Now zero the counter. Animate and time how long it takes for the apparent position of the sun relative to the background to return to the same position. How did this value for the sidereal period of Mars agree with your value from the question or the table in question 12? So let's take a look here. We're going to go back to here. Let's see what it tells us to do again. Put yourself on the planet Mars. We're going to be on Mars. Boom. All right. Now zero the counter and animate. Look at the zodiac strip. So you want to look down here. We're in opposition. We want to look down here. Here's where we are. Here's the sun. Okay, zero that counter. We want to see how long it takes it to get back here again, for the sun to get back in the same position. All right, so let's keep going. Boom, right there. How long did that take? Here it is right here. Answer that question. All right, answer the question. And how does it look for the value of that? Okay, so it says make Earth. We're going to change this to Earth. And we're going to change this to Mars. Boom. Make the Earth the observer's planet and Mars the target planet. Zero the counter and note the location of Mars in the zodiac strip. Animate the planets until Mars, the target planet, comes back to the same place in the zodiac strip. All right, so let's zero out the counter. Mars is right here. We're all together. All right, so let's start that animation and see how long it takes Mars to get back to where we were. Notice it. Did you see the retrograde there? That was pretty cool. Oh, we're going to have to drag this back. Right here. Right here is where we're at. Okay. I'm going to try that again. That just does not. I'm going to try this one more time. Let's pick a spot so we can see it's in the middle of Libra. So let's watch for Mars to get back to the middle of Libra again. Okay. That might be our little clue here. Boom. Mars. Well, let's drag Mars back a little bit. Okay, right there. That's what we want, I suppose, right? So go ahead and then answer the questions, all right? Let's use the simulator to observe the retrograde loops of a superior planet. Set up the simulator for being located on the Earth and viewing Mars. We're already there at conjunction, all right? So at conjunction, so let's put them at conjunction. Boom. We can go like this and put that in there. All right, there's conjunction. We're at conjunction. Set up the simulator, Earth, Mars, zero the counter, and start the animation. How long after conjunction does retrograde motion start, and how long does it last? That's great. Awesome. So let's take a look. We're going to zero this. Now let's watch down here for retrograde motion to start. And I'm going to slow this baby down so I can see when retrograde starts. Don't need to go that slow, I guess, do we? Where's retrograde start? You're going to see Mars slow down. Looks like it's going to start right about here, right? It starts at 0.945 years. And then it starts going backwards. And it says, how long does this last? So 0.954, or whatever that number was we just had. And let's start going the other way right there. So you're going to subtract those numbers to find out how long it stays in retrograde. How long after conjunction does retrograde motion start? And how long does it last? Sentence form answer. And folks, we are done with this lab. I hope this helps you. I hope this helps you. Sometimes teachers expect too much out of students, and I'm thinking maybe that's what was going on. So, anyway, good luck with this lab.